Okay, so now we are ready to continue on in our second part of Module 1. So it's Module 1, Part 2. We did get started on this the last time we were together. So this is going to be the, if you would, second lecture that, that we're going to be doing. So I'm going to pull up our PowerPoint presentation here. And we are now actively working in Chapter 4. So in Chapter 4, the last time we were together, we started talking about position. We're drawing now our kinematic diagrams to scale, and then we're going to be moving the driver and then seeing what the rest of the links will do. We are going to focus on graphical analysis, as I had said the last time we were together, because we're in an 8-week format. And you guys get a lot of practice with, you know, doing equations and the math. We're not going to like do the math and then prove it graphically. We're going to focus on the graphical solutions. If you wanted to explore the analyticals, they're there for you and extra examples, but it's not going to be something that you're going to be required to do for us. Also want to remind you that as you go through the PowerPoint presentation, this is your guide for the chapter. So the things that, that we go over, the examples we go over, number one, during our lecture are going to be part of the practice problems that you have to hand in. So you need to follow along for those. Number two, I do skip over sections. So you're not responsible for those sections. They are not going to be something that we're going to be applying when we're doing the homework and the assessments that we have. So, so make sure that you take this PowerPoint if you're working on it, and it helps you to know where you want to focus your time. So we ended last time with example 4.2. So we are going to skip over to section 4.7 in your book, and it's called Limiting Positions Graphical Analysis. So this starts, let me see here, 4.7. Where is 4.7? Oh, here it is at the very bottom. It's kind of starts in a weird spot. I'm just going to show you in the book where it's at. If I go underneath here. So at the bottom of page 87, okay, the bottom of page 87, right down here, this is where section 4.7 starts, limiting position graphical analysis. So I'm going to kind of put this aside and we're going to go to our PowerPoint, kind of work through things here first. So first of all, the configuration of a mechanism that places the follower and the links in an extreme position is called limiting positions. So what this means is we want to figure out what is the furthest and the closest position of our output based on the kinematic diagram that we have. Most of the time when we draw, for instance, our initial position of our kinematic diagrams, they're kind of like mid-cycle, if you would. We're not really at one end or the other of the operation. So limiting positions do exactly that. We figure out, okay, what is the extent of that output, the furthest away and the closest. Now, there are two things that we're going to be looking at. Number one, what is the limiting position when we look at linear displacement? And that is going to be called the stroke. So the stroke is going to be the difference between the furthest and the closest point when we have a slider that we're interested in knowing what's going on. So it's very similar to a piston in a cylinder. Like, what is the stroke of that? It can be a pneumatic cylinder, it can be a hydraulic cylinder, but stroke is a very common measure of how far, or that difference between those limiting positions, the furthest and the closest point. So if we look at figure 425 in our book, that is at the top of page 88, right up here. So I'm going to zoom in. And what we have here is we have a kinematic diagram. We've got it actually in 3 positions, okay? The first position, or the home position, if you would, is going to be wherever we see just the letters called out. So for instance, A is going to be the same letter all the time because it's not a point that moves, and it's actually the point for where the crank is going to be rotating around. So it's a fixed point. But you'll notice that the position B at the end point of the crank, which should be link number 2, it's in its like just B form, and then it's connected to C. So right here is just kind of the kinematic diagram in like a random position somewhere within the cycle of, you know, a full rotation of that crank. Now, limiting position work, what we want to know is, okay, this is connected to a slider up here. How far out along that slider's path and how far in, if you would, would those extents actually go? So what's the furthest point and what's the closest point when we move this crank around 360 degrees, okay? So you'll notice that what they do is they show these limiting positions. The first limiting position they have is going to be the closest position. So you rotate this around and you're going to notice that we have B prime. B prime is like, if you would, the second position. So if this was the original, our second position is going to be B prime and C prime. So you'll notice what that does here in this position. This is the closest that that slider is going to be, or the furthest to the left. Then we continue to rotate and we find, okay, where is the furthest out position? And that's going to be the B prime prime and the C prime prime. So the difference between those two extremes, or those two limiting positions, is what we call the stroke when we're looking at linear displacement. So along a straight line, linear displacement. Okay, so sliders are the ones that are going to be described as their limiting positions as the stroke, the total difference between those two positions. Okay. So any questions about that right now? Some of you who have maybe worked around cars, stroke is a very common term that's used to let us know what that is when we look at like cylinder displacement. Back over here. So let's look at example 4.6, which is going to be an example of limiting positions on a slider mechanism. So we're going to go through this process. We'll kind of bump back and forth here. But as we know, whenever we're starting any of these problems, the first thing that we're going to be doing is drawing our kinematic diagram and determining what the mobility is, or I like to say confirming what the mobility is. So, so that's going to be step number one. So let's go underneath our camera. And as we look at example problem 4.6, we're going to notice that we have a reciprocating saber saw here. We want to determine the configuration's limiting positions. So let's kind of look at the mechanism first. You're going to notice that we have a reciprocating blade down here. That reciprocating blade is going to go up and down, and it's going to be vertical in a straight line motion. So that means that that's going to be represented with a slider. Now, as we work backwards, the connecting rod is going to be connected to what would be a flywheel here. Okay, and at the center of the flywheel would be the center of rotation, or if you would, the frame for which that flywheel is going to be mounted and connected to that connecting rod. So we are going to, number one, draw the configuration of our kinematic diagram in the position that we see here. Now, we're given the information that we need to draw this to scale. So I'm just gonna kind of reference over here. This is going to be the diagram that we're going to be creating. The dimensions are going to come from the original diagram here. Okay, so what I want you to do is I want you to go over to AutoCAD, and I'm going to do this kind of alongside you. I'll let you guys work. I'll kind of put mine in position, and then we'll, if you would, meet up and compare our diagrams, and then we're going to move to the next step in the process, which would be calculating the mobility. So go ahead first and create your kinematic diagram on AutoCAD with your start file first, using the diagram that we see here. So I'm gonna switch over to my AutoCAD here. I'm not going to talk through this process. You guys have done this quite a bit already. So I'm gonna let each of us work independently, and then we'll get it in order, and we'll kind of continue with the problem. Now, again, we're drawing it to scale, so make sure that you use the dimensions in the diagram on page 88. Don't forget to resave your kinematic start file to the example that we have here. So I'm doing a save as, and this would be example. right, anybody still working? Okay, that's all right, take your time. And don't forget to do a quick save after you get this in position, because we don't want to lose the work that we already have. I'm going to start kind of moving on to our next step here. And talking about how we're going to figure out the two extremes for each of the positions. So as we look at the diagram at hand, okay, I'll wait for everybody's attention. I want to make sure, even if you're not quite here, it'll always be time to catch up after we're in lab. But where we're at right now, you're going to notice that we have this slider in kind of this random, it's somewhere inside of the cycle. When we talk about cycle, it's one rotation of that crank as it goes all the way around. Right now, it's kind of in, somewhere in the middle of that cycle. We want to find out what is the furthest position down and what is the highest position up, okay? Now to do that, we can do there's two simple calculations. We're going to use the length of each one of the links that we have. I'm also going to let you know that kind of from here on out, we're always going to have the following sequence of our links. Link number 1 will always be that frame, no matter what. Link number 2 is going to be our crank or input. Link number 3 is going to be our connecting rod. And link number 4 is going to be our output. And in this case, it's going to be the slider. Always, okay? 4-bar mechanisms, link 1 frame, 2 crank, 3 connecting rod, 4 is going to be the, in this case, the blade going up and down, but it's going to be your slider or your output. It's going to be whatever your output link is, because it could be an oscillating link as well. Now, what we're going to do is we're going to take the lengths of links numbers 2 and 3, and we're going to add them together to get the furthest point out. So what that does is it takes the link number 2 and link number 3 and puts them in line. And we want to know, okay, if we take that distance from the center of rotation of that crank, how far down is that going to be? So if we look back, link number 2's length was 1/2 inch, right? And link number 3's length was 1.75. So we're simply going to add those two together, okay? So 1/2 inch plus 1.75 is how much? You can do it on your calculator if you need to. 2 1/4, 2.25, right? Now, what we're going to do is we're going to go back to AutoCAD. We know that this slider can only go along a line of action that is vertical. So we are going to, I'm going to change my layer to Object 2 so I get my hidden lines for my second position, okay? And what I'm going to do is I'm going to take a line and I'm going to go through the center here, and I'm just going to draw a vertical line going straight down, just a random length. This is representing the path that that slider can take going down. Okay. Now, using that number of 2 1/4, I'm going to draw a circle radius. The center is going to be at A, which is the center of rotation, and its radius is going to be 2.25. Okay. And where it crosses that line of action for the slider is going to be the new position. Okay. So I am now going to draw everything so that I have my slider in that furthest down position. So go ahead and redraw everything here so that we can see this in its new position. So I'm going to kind of on the side here, move this down. We did this the last time we were together too. So make sure you're doing a copy. We want to leave what was there originally. And you might have to move around some of your labels and stuff because they're probably not going to be exactly where you want them to be anymore. And then we're going to do a line from here to here. And then you're going to change the call outs for the joints to have the prime in back of them. So our new position of point C is going to be C prime. Our new position for point or joint B is going to be B prime. So I'll let you guys catch up. Just make sure that you show the joint here for B prime along that line with a 1/2 inch radius from that center of rotation. And now you can see that those two links are in line with one another, which would give them their furthest position going down for that slider. So the position that we have here at C prime is its lowest position. Okay, so that's going to be one of the limiting positions or one of the extreme positions of our output, which is in this case, the blade of that saber saw. Okay. Any questions so far on that second position? Okay. Now we are going to be adding a third position. So what that means is we're going to have to add another line type or color, if you would, to our layers. So we're going to go into layer properties and I'm going to click on object 2. I'm just going to hit enter and I'm going to call mine object 3. Okay. I'm going to change the color. I'm going to call it cyan because again, that's for me, I've got a dark background. It's easy to see. If you pick colors that I cannot make out the difference, if you're picking dark colors if you have a dark background or light colors, if you're on a light background, when you do your screen snips, if I can't see them, I'm not giving you credit. Okay. Because again, I want you to have the eyes of your presentation of what you're handing in to be something you would present to somebody to show them what you did. And if they can't see the lines, then neither can I. Okay. So, so make sure you're using that as kind of your criteria. I'm going to keep the line type 2 hidden just so that it's different than my original. And because I'm going to have the cyan different than the green, we should see those, those differences. You'll see those colors when you do your screen snip. So I am going to leave it at a hidden line type. So I'm just going to close that. And then I'm going to change, my object line or my layer to be my object 3. Okay. Now I'm going to do the other extreme position. Now the other extreme position, I'm going to go back underneath here, is going to be when this rotates back over and I have the connecting rod overlapping with the crank, okay? So that means that I'm actually going to take the connecting rod dimension L3 minus the length of L2. So that would be 1.75 minus a ½ inch. What would that dimension be for us? .25, exactly. So now from that center of rotation, we're going to do that same process, but with a different dimension. I have my object line on here. I'm going to draw a circle radius from my center of rotation of 1.25 this time. And then I just need to, and I'm going to draw a line from where it's at right now. And I just need to draw a vertical line until it crosses over that radius that I just created. That's going to be the new position, the upmost position of my slider. So now I'm going to move everything so that it reflects that. So I'm going to copy this and that to go from where it's at up to the intersection up here. And then I'm going to change that to object 3. I'm going to copy C, and this is going to be C prime because this is the second version of this that we have. That's going to be its center. And then we're going to go back to the center of rotation for link number 3. So it's going to be a line from here to here. And then along that length, along that very same line, with a radius of 0.5, we're going to extend, oopsie, did I get the extend? I think I did. Extend this line all the way to that radius of a ½ inch, okay? And then my new position of B prime, oopsie, is going to be back over here. Okay. And then I'll copy B, and this will be the new. I'm going to have to move things around so that it's easier to see. So there's B prime. So I'm going to get rid of my radius, get rid of this radius. Those were just for construction. And now that's the new position of the highest position. Okay. So I am going to do a little bit of maneuvering here so that it's a little bit more clear on what we've got going on. I'm going to move A down. I'm going to move number 3, maybe over here closer. And again, making sure these are readable. So when you hand this in again, I don't want to have to try to make assumptions on where things are at. Let's see on this side. So now once we have our limiting positions drawn in place, how am I going to get what the stroke is? Remember, the stroke is the difference between the highest and the lowest point, the two extreme positions. How would I get, and how would I determine right now what the stroke is? So how would I determine what the distance is between the highest point C prime and the lowest point C prime? What could I do? How do I get the distance? How can I show the distance? Nope, I'm not going to do any math. I can do something in AutoCAD here to show the difference between that high and that low position. What could I do? Just dimension it. Exactly. So you're going to add a dimension for this answer. So you're going to go to the notes. Okay. Make sure that you change your layer, and you're going to use linear dimension, and you're going to go from the center. Make sure you grab the center of the top one to the center of the bottom one. And we are going to push this over here, and then I'm gonna have to move my points again because we don't want to be going through the center. Now, although this is not technically a drawing, I want to remind you that what you are handing in is something that is going to actively answer the question of what is the stroke. So I don't want dimensions that are overlapping, or I don't want dimensions that I can't see the numbers, okay? Depending on the scale of things, I want to make sure that whatever screenshot you have, I can see everything. And if you have to change the scale of the dimensions, you guys know how to do that, okay? So this is what the stroke of our the reciprocating saw blade would be. So what are the limiting positions? And then what is the stroke? Okay. Let's look back at our PowerPoint presentation and just review the steps we went through. So we drew our kinematic diagram. Oh, we didn't do the mobility equation. We got to add that. So we will go back and do that just to be sure. I'm confident it's one, but we want to make sure we get that. Then we want to calculate the furthest extreme and the nearest extreme. So we did that adding link 2 and link 3 to get that radius, and then we subtracted link 2 from 3 to get the nearest or the highest point in our case. Then we struck arcs about the center of the driver to get the intersections with the path for which that slider was going to be on. Then the difference between the two was going to be that total stroke, which we identified with our dimensions. So there's one more thing we have to add, okay? And we need to do the mobility equation here. Now I'm going to go underneath my screen. Now, again, you have the choice on how you want to show your mobility equation, but you do need to show it each time. Whenever you draw a kinematic diagram, automatically assume you have to do the mobility equation. So our mobility equation, and this is for example 4.6. Our F is going to be equal to 3 times n minus 1 minus 2 JP. Again, we don't have any higher order joints here, so you don't have to even put the 0, just truncate it at this point. We'll be worrying about that later on. So we're going to have 3 times, what does my n represent? What is that n variable in my mobility equation? The number of pins. Sorry, Emily, no, that's the other one. That's the other. The joints are the pins. That's going to be my JP. That's going to be number of pins. N is going to be the number of the other one. Nope, not the number of joints. Nope, not the number of joints. The links. N is the number of links. I know. So N is the number of links. JP is going to be the number of primary joints, which pins are joints. Okay. So if we look back at our kinematic diagram, how many links do we have? How many numbers with circles do we have here? Just 4. Yeah. So we're going to go back. So this is going to be 3 times 4 minus 1. Okay. Minus 2 times my primary joint. So this is where I'm going to look back and I'm going to say, okay, how many joints do I have over here? How many letters do I have identified? Don't count the primes. 4, A, right? B, C, and don't forget D on a sliding joint. Okay, a sliding joint is a primary joint, not just pins. Pins and sliding joints are primaries. So we're going to go back over here, and that's going to be 2 times 4. So in parentheses here, we have 3, right? Times 3, that's going to be 9 minus 8. Our F is equal to 1. All right. Now, again, you can either handwrite it and scan this as part of your submission, or you could put it over here on the side. Make sure that you label this as example 4.6. So when you take your screen snip and you submit it as part of the practice problems, that's all there and I know which one it is. If you don't add example 4.6 on here as a label for your screen snip, or you don't identify it in however you're handing it in, I won't know. I won't know what it's for. Okay. So make sure that you're complete and you pay attention to those little details. Any questions on example 4.6 here? Okay, let's check our value. Okay, so at the end of this problem, I'm gonna go back underneath here. You're gonna notice that they have, if you would, a screenshot of how they created the extreme positions here. So they did it in the very same manner that we did. And you're gonna notice that their total displacement, linear displacement, was 1.2656. And if we go back to our AutoCAD, looks like that's the very same number that we have. So very accurate when we're doing things on CAD, as we know. Okay. All right. So that's our first extreme positions example. Let's, I'm going to do a quick save here. Make sure I have that. And I'm going to go back to our PowerPoint presentation. And we're going to look at another example. This time, we're going to look at example 4.7. Okay. This is on page 90. This is another 4-bar mechanism, but oopsie. But this time, we don't have a slider involved as our output. We have a link that's going to rock. So let's look at this problem statement. It says, this is the linkage that operates a water nozzle for an automatic car wash. Determine the positions of the mechanism that places that nozzle, this right here, in its extreme positions. So in this case, this nozzle rotates or pivots around a fixed center. Okay, around a fixed center. So we're not going to have a slider as the output. We're going to have a oscillating link. When we try to find the extreme positions of an oscillating link, it is not called the stroke. Stroke is for linear displacement. Okay, that's the terminology that we use. Throw is for angular displacement. So we want to find out, what is the maximum throw? What is the angle, the highest position, the lowest position for which this is going to operate, okay? And by knowing that, then we can kind of, figure out, is that going to be high and low enough? Is that extreme going to cover the range of the vehicles that we're expecting to come through our car wash, right? Okay. So, so right now we can see that we have our kinematic diagram or our mechanism in just a random mid-cycle operation. So if we're up here, this is our motor. This crank is going to go around in a full circle. So this is going to be our crank. This is going to be our connecting rod. And this is going to be our output link. Okay. Go ahead and draw the kinematic diagram. If you want to peek down below, go ahead and do that. But draw the kinematic diagram using AutoCAD for this 4-bar mechanism and the dimensions that we have here. And I'm going to do that in the background as well. Make sure that you open up that start file and then resave it as our new example 4.7. Now I'm gonna wait personally to put my links on. There are gonna be 4 there. But I'm gonna kind of wait to put those in place until after I've moved my items where they need to be, so that I'm not, repositioning them all the time. So I think I might just put 1 in place, but that'll be it. I know 1 is my frame. So I have my my kinematic diagram done for approximately the position that's here. We really don't know what angle that driver is at, which is our link number 2 here. So that kind of dictates this. But we still can do, we can put it in position here just as a random mid-cycle operation. And then now we're going to put it in its extreme position so that we can see the extent or the throw of that link number 4. Okay, before we move on, let's do our mobility calculation so that we don't forget it like we did last time. So I'm going to go underneath, okay? And for example, 4.7 this time. $4.7. I'm going to do my same mobility equation. F is equal to 3 times n minus 1 minus 2 JP. You always have to write out the equation in variable form. If you're not following along with me, I'm assuming you're like, I know exactly what she's doing, and I'm going to make sure that I do it for my problem. Okay. Don't forget this. Then we're going to fill in our values. 3 times number of links is our n. So we're going to go back over here. Now I didn't number my links, but I know that my frame is going to be number 1. My crank is going to be number 2, connecting rod number 3, and then my output nozzle is going to be number 4. So there's 4 links here, right? So that's going to be 4 minus 1, oopsie, minus 1, minus 2 times my primary joints. Now here we don't have any sliders. So our primary joints are going to be all pins. So the first one is going to be A, B, C, and D. So that's 4 primary joints. So I'll go back over here, 2 times 4. So my F is going to be 9 minus 8, going to be 1. Okay. Yep, I know it's the same, but what's important here is, again, it's the confirmation that you have the appropriate labels and the links called out. So any questions so far on kinematic diagram and the mobility equation, for example, 4.7. Okay. Back to AutoCAD. All right. Now we're going to put it in the 2 extreme positions. So actually, I'm going to move my link designations over just so it's easier to understand. So this is my link number 2, and this is my link number 3, and this is my link number 4. I'll end up moving them, but that's okay. That's okay. All right. So now as I want to look at the extreme position. So if I go back to my, my PowerPoint over here, go here. The 2 extreme positions are going to be identified by either adding or subtracting links 2 and 3. Okay. So we're going to look at the furthest extreme position. We're going to take link number 2, the length of link number 2, and we're going to add it to the length of link number 3. So if we go back to our illustration in the book, okay, link number 2 is right here. That's 0.75. Link number 3 is 2 inches. So for the furthest position away, I'm going to add those 2 together. That is going to give me 2.75. So now I'm going to change to object number 2. Oh, that's right, because I didn't do it. I'm going to do a radius from the center of rotation, and this is going to be 2.75. Okay. 2.75. Now, this is to find position of C. Then what I need to do, there's not a line that this intersects with this time, right? I have to find the point of intersection. I know that link number 4 is 2 inches long, right? So I'm going to do another circle radius from that center of rotation. And how long is this radius going to be? 2 inches, right? 2. So now where those two circles intersect down here, that's the furthest down position. Okay. So this is where my C is going to be. So I'm going to copy the C. Now I'm not going to copy the link because that's just going to move down. I'm going to redraw that link, but the point C, I'm going to copy. So I'm going to go from, make sure you get the center to the intersection. This is my new position, C prime. Okay, it's its furthest down position. Now the link is still gonna rotate about the fixed center at D. So I'm simply gonna draw a line from the center at D to the new center at C prime. Okay. And I am going to erase this radius right here. I'm going to keep this one because that one's going to come in handy for my next one. Okay. And then I'm going to draw a line from A all the way down to C prime. Okay. And I need to show where B is. B has a radius of 0.75. So I'm going to draw a circle with a radius. Do you guys notice you do circle radiuses all the time on here? 0.75. So this position where this intersection is with that line, that's going to be our B prime. So these, that center to that intersection. Here again, I gotta move my B prime. I'm going to get rid of the circles for right now so we can see. Oops. I didn't want to do that. Undo. I just want to erase this circle and that circle. There we go. Okay. So here are my new positions. So my C prime is down here and my B prime. Notice that my link number 2 and my link number 3 are in line with one another. Okay. Any questions on that position? I'll give you a minute or two to get it so that it's where I've got it here. Virtually, you guys doing okay? I don't see any comments, so I always think of it as no news is good news, and that's okay. All good. Thank you, Tyler. Still good. Emily's thumbs up. Awesome. Thank you. Thank you. Okay. Now, the other position that we're going to do is going to be the furthest up. So we want to figure out, okay, where is this one going to be? And to do the other one, we're going to, whoopsie, we're going to use the other equation. So this is going to be the length of L3 minus the length of L2. So L3 in our case, again, is going to be the connecting rod 2 minus 3/4 of an inch. So that's going to be 1 1/4. So we're going to go back over to AutoCAD. Oops, back over to AutoCAD. And I need to add my layer in here, layer number 3, or object line number 3. I'm going to change it to cyan. Okay. Rid of that. And then now I'm going to draw the radiuses that I need for this one. So I'm going to draw in from the center of A, that radius of 1.25. And I'm going to change it to object 3. Okay. And I'm going to get my current layer on object 3. Okay. And then I need to do my radius of C, which is 2 inches. And I'm going to find the intersection, which is right here. It's not going to be this back intersection here. Okay. It's going to be the front intersection. It would be the extremes on this side. And now that's going to be my new position for my C prime prime. Okay, right there. So I'm going to grab my point, my pin and my C. I'm going to change this to C prime prime. Okay. And I know that I'm going to do a line from the center of rotation at A to C. And then I need a radius of 0.75 because now I'm going to extend that line back to that radius. So I'm going to use the extend this way, that way. Oops, come on. One more time. And that'll be my new position for B prime prime. Grab this guy. Up there. Change this to prime prime because that's the other extreme. And then I'm going to get rid of all my construction radiuses here. Enter, not escape. There we go. And the last thing I need to do is draw my link number 4 from D, C to C. And I have to move my link designations and such so that I think I can see them all now. There we go. I'll give you a minute to catch up with that. Making sure to change your labels for this second extreme position to the prime prime. So B prime prime, C prime prime, and then connecting, you know, where they're going. Now, even though I have these in the extreme position, okay, and that's what we just constructed, what am I actually looking for in this problem? What does it want? What does it want to know? What is the angle, right, between the low and the high position of that nozzle? We want to know, like, what is the sweep or what is the throw angle of the extreme positions for link number 4 or that nozzle? Okay, so how would I find that? How would I graphically get that from AutoCAD here? How would I find what is the throw? Well, last time stroke, what did I do? I dimensioned it, right? So what am I going to do this time? I'm going to dimension it. Now, this is the thing. This is an angular displacement. So we cannot use a linear dimension. Don't use linear dimensions. A lot of students make this mistake. So if you're not listening to me right now, this is a good time to come back. All right. Do not do a linear dimension from here to here. Don't do that. That is not the answer. This is an angular displacement. So we need to use what type of a dimension? An angular. Yes, exactly. So I'm going to do an angle and I'm going to go from the highest to the lowest. Don't use the one that you did in between. Now, you are going to notice that the standard is to just have 0 decimal places, but we want a little bit more accuracy. All right. So what I want you to do is you are going to go to annotations underneath here. And you're going to go to dimension style. Okay. Dimension style. And we're going to go to modify. And we're going to go to the tab on the top that says primary units. You are going to change this precision for the angular dimensions to 3 places. Okay. I want to see your dimension to 3 places. You're going to hit OK. If you don't do this for your practice problems, that could be one small thing wrong. And if you go over 2 small things wrong, you get a 0 instead of a 10. All right. At this point, you guys are second-year students. I'm expecting you to be following along and paying attention to these little details. Make sure to set that as current, and then you can say close. And now you should get 3 decimal places on that angle. So 47.0008. If you leave it at 47, you might be like, it's close enough for Kelly, but Kelly's saying, no, I want you to change to 3 decimal places. That's part of this practice. Does everybody get the 3 decimal places, the same number that we have here? Everybody? Asking everybody in the room. Everybody get the same decimal places here that I have for the angle? Okay. Virtually, did you guys get it too? 47.008. Yes, thank you. Thank you. Good, good, good. All right. Then what we want to do is if our dimension interferes with some labels, make sure that you move like the C prime prime. We're going to move that over so that it's not going through the line. So even though, again, I'm not looking for ANSI dimensioning skills here, you're going to be showing this to somebody, showing them what you found out about the layout work that you did. So you want it to look neat and easy to follow. That's what I'm looking for when you hand it. Okay. So do a quick save on this, file save. You can get rid of the X, Y, and the extras down here. And remember, as part of the screenshot that you're handing in, make sure that I know that this is example 4.7. So you're going to write the text here on the side, or when you pull it into a document that you're labeling it there. Whether you are handwriting or adding it to the illustration here, I want to see your mobility calculation that you got a value of 1. Okay, and then that you have all your labels here with, especially the 3 for B's, B prime and B prime prime, and then C prime and C prime prime. That lets me know the extremes that you're going through. And then also the color changes so we can see which are the original, the furthest, and the nearest. All right, so do a quick save here. All right, that was example 4.7. Let me look at our PowerPoint presentation. We got there. And then our next subject is going to be displacement diagrams. We're going to stop and take a break, and then we'll be back and we'll continue on with displacement diagrams. So I'm going to actually stop the recording.